Good afternoon, everybody. Welcome to BSides Las Vegas Breaking Ground track. This next talk is called State of DNS Rebinding, and our presenters today are Gerald, Doussot, and Roger Meyer. A few announcements before we get started. We'd like to thank our sponsors, especially our Inner Circle sponsors, Critical Stack and Valimail, and stellar sponsors, Cylance, Microsoft, and Robinhood. It's because of the support of these sponsors and our other sponsors and our volunteers and donors that we're able to do B-Sides, so thank you. These talks are being streamed live, so as a courtesy to our speakers and to everyone else in the audience, we ask that you leave your cell phones on silent position. At the end, if you have a question, please raise your hand. I'll bring you the mic. We want to be sure and get your question on the microphone so that the YouTube audience can hear it. And that's it. With that, let's get started. Here's Gerard and Roger.
Thank you. So today we're going to discuss the current state of DNS rebinding, including recent attack and prevention techniques. We will discuss our new tool, Singularity of Origin, and how it incorporates this new technique and how you can use them today. So our contribution in the domain of DNS rebinding are twofold. One is our new tool, Singularity. It includes everything you need to perform a DNS rebinding attack. It is reliable, performant. It includes built-in payloads for common services and allow you to perform automatic service detection and exploitation. The second area of our contribution is in the research of improving the speed of DNS rebinding, how to bypass common DNS protection, rebinding protection. So our talk is focused around our tool and these new techniques. We will include a customary DNS rebinding refresher, and we will also discuss HTTP proxy-less architecture to browse the victim internal network. So who are we? We are Gerald, Doussot, and Roger Meyer. We are security consultants at NCC Group. We are attached to the San Francisco office in California, and we are the authors of Singularity of Origin. Roger?
Why should you care about DNS rebinding? Most developers understand that when they bind their web application to all interfaces, they expose their application to remote access, and they see that this is not a good idea. So what do they do to fix this? They bind the application to the local host. They think this is a trusted environment. They don't need authentication because only local users can access, right? And then all these DNS rebinding issues happen. The EOS cryptocurrency wallet was vulnerable to DNS rebinding. The Google Home, Roku, Sonos speakers were vulnerable. The Geth Ethereum client, Redis, Memcached, Elasticsearch, Kubernetes dashboard on Minikube was vulnerable to RC and VM escape via DNS rebinding. The Rails web console was vulnerable. We see more and more applications exposing an HTTP server on the local host, especially through the popularity of frameworks such as Electron. The rise of IoT devices exposing sensitive interfaces on internal networks without authentication will make this even worse. And then we would like to clear up certain misconceptions, such as that DNS rebinding is slow and can be solved by out-of-the-box DNS filtering products or solutions, which is not the case. We would like to start with a quick refresher on how DNS rebinding works. The origin consists of the scheme, host, and port. Two documents share the same origin if they have the identical scheme, host, and port components. The same origin policy is an important security concept implemented in browsers that dictates how two different origins, two different websites can interact with each other. Certain interactions are allowed between all origins, such as forum submissions, links, redirects, content embeddings. Cross-origin reads are typically not allowed. This is important if you're logged into gmail.com, for example, and browse to an attacker-controlled site. You don't want the attacker to be able to read your Gmail messages. DNS rebinding permits us to bypass this same origin policy. Let's start with a visual walkthrough to show you how such an attack would work. We have the victim, the browser. We have a target service. This can be a service listening on the local host, as shown here, or another service listening on the internal network. On the right side, we have the attacker, which consists of a DNS server and a web server on this public IP. So on the right side, we have the internet, left side, intranet. The victim can access the target service without authentication. That's a requirement. And the attacker cannot directly reach the target service. Otherwise, we wouldn't need DNS rebinding. Step one, the victim browses to the attacker's web server. This creates a request to rebind.it. That's the domain name, the origin where we are hosting our attacker web server. We respond with the public IP address, and we return some JavaScript, which keeps running in the browser and waits until the DNS record expires. Once it expired, we create another request. This time, we respond with a different IP address, the IP address of our target service, 127.0.0.1. Notice that the origin, rebind.it, did not change. So the JavaScript, the browser, will make this request, and the browser will allow us to read the response because we did not violate the same origin policy. The origin is still the same, and we can then exfiltrate the data back to the attacker. This was a high-level overview, which omitted a lot of details. Some of them we'll go over. If you want to know more details, there are a lot of previous really good presentations which go into much more detail. We would like to start with our first demo. This is a demo on Safari on iOS, showing that DNS rebinding can be done in just 5 seconds on iOS using the cache flooding technique. We will be targeting a home router on router.asos.com. That's the target. And we will read the response of the index page and display it in a JavaScript alert pop-up for demo purposes. So this is Safari on the latest iOS. We're browsing to the target router. That's our target. Now we're setting up the attack. We're going to the Singularity Manager web interface. We're setting the target to router.asos.com. We are leaving the target at port 80. We are setting the attack payload to a simple fetch get. We are using the rebinding strategy first and second, an interval of 1 second, and we're enabling the cache flooding. We start the attack. This takes just 5 seconds, and we should see the response. This pop-up just displays the response of the index page. It's a redirect to main login.asp, but it shows that we were able to read the response from the router.
Thank you. So now that we have a grasp on the basics of DNS rebinding, we are going to show how we were able to make DNS rebinding attack more reliable in Singularity. So let's say you're a fan of horse riding, and you are trying to organize your vacation around this theme. So you visit this website, and it has a Trojan horse picture displayed here, nothing wrong. In fact, the site was compromised, and it's running a hidden iframe for Singularity. So you connect to the website, and you download the malicious JavaScript code from Singularity, and the code emits its first DNS query. So what's in a query? The DNS query sent by the browser to the Singularity server is made of several components. These components encode all the information that Singularity needs to perform the DNS rebinding attack. So first, you have a start tag. It is followed then by the IP address of the attacker host, in this case, Singularity. Then you have the target IP address or DNS name. You have a session ID. The session ID, so the sessions are used to support multiple user or victim and services. Then you have the DNS rebinding strategy, in this case FS, first then second. Singularity include a number of DNS rebinding strategy. We're going to cover some of these later. First then second is also known as a time-varying attack. It is the most reliable and the easiest to implement attack you can perform. Then you have your end tag, and you have your attacker host domain that the attacker may have purchased or have compromised. So to improve the reliability of DNS rebinding attack, you want to disable all form of HTTP caching, and we do that for all browser implementation in intermediary cache. So that ensure that the target browser always fetch fresh copies of resources. We also instruct Singularity to drop idle connection from target browser. So when DNS rebinding time is happening, the browser doesn't stick to the attacker server, but switch to the victim service. What about TTL value? Most literature and tools around DNS rebinding implements a TTL value of 1 second. We used 0 in the hope that it would break stuff. However, it didn't. That was disappointing. But 0 is a very valid value, so we stick with it. So how do we figure that DNS rebinding has happened? How does the browser figure it out? Historically, Singularity used an index token embedded into the HTML web page to detect whether it is pointing against Singularity or against the target service. We recently moved into making this data in the HTTP header. So if the JavaScript code that was downloaded on the target browser see this header, it knows that it is pointing against Singularity. If it doesn't see it anymore, it means that the rebinding has successfully happened. Note that we still use the index token in some circumstances, especially in multiple DNS rebinding strategy that we were going to cover shortly, where the Singularity will drop the connection to the target browser very abruptly. The browser gets confused, and the index token is one way to detect that it's pointing against Singularity or the target service. Another thing you need to consider as well is that when you perform your attack, you may be facing an environment that includes IPS and IDS. These IPS and IDS may emit spurious DNS queries of their own, which mean that the response might be out of sync, and that the target browser will never see the IP address of the attacker server in its response, meaning that they cannot get the malicious JavaScript to perform the DNS rebinding attack. So to cater for this type of environment, we implemented a random DNS rebinding strategy where Singularity will reply randomly either with the attacker IP address or the target service. So it's a much slower technique in general, but you could get lucky. So we're going to cover now how we improve the speed of DNS rebinding in the Singularity. So DNS rebinding speed vary on the number of, based on the number of elements, including whether you use a Windows or Unix-like operating system, such as Linux or macOS. The browser vendor, obviously, i.e. Edge, Firefox, Chrome, and Chromium, and all their spin-off, including the recent version of Edge, Safari. The target specification as well matters, whether you specify a service on the loopback interface, or whether it's on the private network, or it's a remote public IP address. Obviously, external factors such as the spurious DNS queries may slow down the DNS rebinding. So just to illustrate, DNS rebinding may take up to 40 plus minutes on edge, and with the appropriate strategy, you can reduce that to 3 seconds. Singularity can automatically fingerprint to optimize for speed in certain circumstances. We're going to cover this shortly. So the time-varying attack that we implemented in Singularity typically take approximately 60 seconds to rebind all browsers except IE or Edge. So we implemented another rebinding strategy called multiple answers. Multiple answers, we thought it was not going to work originally. There was some paper stating that it would work in certain circumstances. And one of our colleagues, Michael Roberts, made a quick proof of concept, showing us it was working very well on Windows with a target IP address set to 127.0.0.1. So we implemented this, and we got a 3-second DNS rebinding time on Windows. However, this didn't work on Unix-like operating systems such as Linux or macOS. But after digging, we found out that when you set the target IP address to 0.0.0.0, then you get the same 3-second rebinding time for Linux and macOS. This means that we have a solid and fast DNS rebinding against whole localhost type of services. Just to illustrate at a high level how the multiple answer rebinding strategy works, so the target browser will emit its first query to the attacker server as usual, but where the first and second or time-varying attack will reply with the attacker IP address first, then the target's IP address, the multiple answer rebinding strategy will respond with both IP address record at the same time. Then the target browser will poll Singularity to determine whether it's still pointing against the attacker server or the target IP address. After a while, Singularity will implement a dynamic ephemeral firewall rule that will block the requests from the target browser to itself. This will force then the target browser to use the second IP address that we sent initially and then point against the target service. So multiple answer work very well with the loopback interface, as we said, 0.0.0 on Unix type operating system and 127 on Windows. However, we were getting inconsistent results for our target specification. For instance, it will work only 1 time out of 5. So we implemented another technique called DNS Cache Flooding, so this technique works well on Google Chrome, on all operating system, and on Safari or on iOS platform. So we observed DNS rebinding time with the time varying attack and DNS cache flooding at the same time from 5 to 40 seconds. The demo that Roger performed on iOS was using this technique, and we obtained a 5-second rebinding time. Flooding of the cache is performed separately in a web worker. So basically, what's happening in blue here? So we are in the browser console, and you can see that in blue we're performing the regular fetch against Singularity, and between all this fetch, we're sending thousands of DOMI requests for resources that will flood the cache of the browser and will evict, once the cache is full, evict the Singularity IP address. So the only IP address that remains is the target IP address, which will facilitate the DNS rebinding. So here we have illustrated a number of target specification and platform and strategy combination, and what you can expect as a time to exploit in seconds. So for instance, on Windows 10, if you use the multiple A strategy, it takes approximately 3 seconds. Roger?
Okay, let's talk about DNS rebinding protection bypasses. Using Singularity, we can bypass all known DNS rebinding protections, such as those implemented in Unbound or DNS masked open source DNS servers. We would like to emphasize that common recommendations and default configurations often do not provide complete protection. How do common DNS protections look like? Most solutions block certain DNS responses at the perimeter when they enter your internal network. Some solutions block RFC 1918 IP addresses commonly used internally, such as 10/8 or 192.68/16. Some block localhost IPs, the 127/8 range. Some tools can be configured which IP addresses you're using internally. If you're using public IPs, you can configure those to be blocked. Some tools block the 0/8 range. DNS Mask and Unbound are widely used open source DNS servers. They are used in tools such as pfSense, OpenWRT, certain home routers have them. There are also free public services, DNS services, such as OpenDNS, which advertise that they have a solution for DNS rebinding attacks. In case of OpenDNS, they call it block internal IP addresses, and they block private IPs. DNS Mask has a configuration setting called Stop DNS Rebind, which blocks private IPs, the 0/8 range, and the 127/8 range. This does not block localhost. We'll talk about what we mean by that localhost in a minute. The Unbound open source DNS servers. DNS server has a configuration called private address, where you can configure the internal IP address range you're using, and then blocks this range. This does not block the 0000 IP, 127.0.0.1, and localhost. Our first bypass is using a 0.0.0.0 IP address. This is a non-routable or invalid IP address, but it works very well on Linux and macOS using Chrome and Firefox to access the localhost. This bypasses protections that block DNS responses containing the IP address of 127.0.0.1. If we look at a DNS request, when we query Singularity, we specify the target here with 0000, and then you return a DNS response containing an A record of 0000. What if all internal IP addresses are blocked? Then we can use CNAMEs. Canonical name records are DNS records which map one domain name to another domain name. We can return a DNS CNAME record instead of an internal IP address, such as wiki.nccgroup.com or jenkins.internal.corp.com, whatever our target name is. This bypasses protections that block DNS responses containing private IP addresses. The local internal DNS server will then resolve the CNAME, and you don't want to block internal resolution if you want to use DNS names internally. If we query Singularity, we can specify the CNAME here, wiki.nccgroup.com, target, and then we return a DNS CNAME record pointing to wiki.nccgroup.com. Our third bypass is using a variation of the previous CNAME. In this case, we can return a CNAME of localhost. This bypasses protections that block DNS responses containing the IP address of 127.0.0.1. This works well on Linux and macOS as well. So we specify the localhost in our request, and then return a CNAME pointing to localhost.
So now we're going to discuss the architecture we implemented in Singularity to indirectly browse the victim internal network after DNS rebinding. So there have been, or there are tools such as BEEF, the browser exploitation framework, and FireDrill, a DNS rebinding attack tool that can use a hooked browser to as a gateway to access environments that are typically not directly accessible by attackers. So we know that BEEF require you or the attacker to configure their browser to use the BEEF application server as an HTTP proxy. We don't know how FireDrill does it because the code is not available. But we decided to implement the browsing of a service via a hooked browser in Singularity without requiring the attacker to set up its browser to use an HTTP proxy. So at a high level, this is how it works. So once the rebinding has happened, the hooked browser will establish a WebSocket connection to Singularity and await for instruction. The attacker will then connect to his browser, connect to Singularity, and list all the targets that were hooked and select one to browse. So what's happening, let's say you want to browse the home directory of service listening on 127.0.0.1. The attacker browser will emit a regular HTTP request to the home directory, but this time to Singularity application server. The Singularity application server will translate this to a WebSocket fetch operation and send this WebSocket request to the hooked browser. The JavaScript code running on the hooked browser will in turn translate this request into a regular fetch API request to the target service, and then we'll send the data all the way back to the attacker browser. So at a low level, we just customize the Golang round tripper interface, which is an interface that represents a request and response, and you can mingle with them. We use WebSocket plaintext protocol to package all the fetch, request, and response between all the parties involved. Noting that this increased the size of the message by 4/3 of the original length of the message because we're using a base64 encoding to package the request and response. You don't have to use your browser. You can use any other user agents, such as curl, or HTTP inspecting proxies, such as burp or zap, or SQL map. So when we implemented this architecture, we encountered a number of challenges. The first assumption that we made that we didn't have to care about cookies, but the victim browser will handle all of this for us in a transparent manner. However, our first test case, Duplicati, which is a backup application, and that was vulnerable to DNS rebinding attack. As you can see in this code sample, extract CSRF token from the cookie. And it does this to generate the link to browse the application. So when we tried this new architecture in Singularity, it didn't work because the link didn't have the CSRF token embedded. So we had to read these cookies from the target browser. So the victim browser is instructed to fetch the cookie from the service and send them to the Singularity server. Then the Singularity server will set them on the attacker browsers. So then the attacker browsers can generate the link with the CSRF token. So that worked well for HTTP-only cookies. For non-HTTP-only cookies, sorry, if your victim service is setting HTTP-only cookies, well, we don't really care because JavaScript cannot read them on the attacker browsers, so they are not being used, so we don't need them on the attacker browser either. Another challenge we encountered is that to be able to read the cookies when we emit a fetch request, you must pass the option credentials includes. And if your application also requires HTTP authorization, then you can completely forget about this. And the reason why is that if you have a simple service that requires HTTP authentication and you're in your console, you can type this command. You do a fetch request to the localhost service with credentials include passed. A authentication dialog box pop up, which will warn the victim that an attack is ongoing. However, if you pass credentials omit to the fetch request, no authentication dialog box will pop up. So the victim will be none the wiser. So the gist of it is that if your application requires HTTP authentication, then we decided not to pass cookies. Roger?
All right, now that Gerald introduced us to this hook and control concept, we'd like to show you a first live demo of how this feature works. If we have working internet. So we will use two browsers. One is the victim browser, one is the attacker browser. In our demo, they're both on the same host, but in a real-world attack, this does not need to be. So the attacker can be anywhere. So this is Chromium, and we have that's a victim browser, which has a Jenkins instance installed on the local host. That's what we are trying to exploit. We have Firefox, and this is the attacker browser. So what you see here is the hooked clients. That means the victims should show up here once it's hooked. And if you reload this page, there's nothing here because the victim is not set up yet. So as the victim, we are setting it up manually again for this demo. We are browsing to the Singularity Manager web interface. We are setting the target host to 0000. This means the local host. We are setting the target port to 8080, where our Jenkins instance is running. We are using the hook and control payload. We are using the multiple answers rebinding strategy, an interval of 1 second, and we are launching the attack now. We see the DNS rebinding is already successful. It just took 3 seconds. We're going back to the attacker's browser, reloads the page, and we now see this new session, the victim session, pop up. So we click on it, and we should be able to browse the victim's Jenkins instance as if we would be able to directly access it and browse to credentials, for example, or anything. And this works over the internet wherever the attacker is, because Singularity here is just on the internet. We would like to show you how the requests look like in the victim browser. Make this a bit bigger. We see here the request to credentials, which the attacker is browsing to. We see the remote address set to 0000 for localhost, and we see the request URL. The origin is still pointing to the attacker. We want to show you also how we exfiltrate our data back to the attacker. This is the SOOWS endpoint. So these are the WebSocket messages. This is how we send the data back to Singularity, where the attacker can then browse to it.
Okay. Now we're going to discuss how we implemented scanning of vulnerable hosts and services in Singularity. So there have been a lot of smart attempts to replicate the power of Nmap or network scanning without the power of raw sockets in the browser. For our purpose, it is often unreliable or did too much. For instance, we don't care whether a port is listening, whether SSH port is open or not. The only thing we care about is does it speak HTTP? because the DNS rebinding so far is concerned with the HTTP protocol only. So this what we're targeting for, aiming for. So our solution is very simple. We use a modern API such as fetch and abort, and wrap the fetch request with a timeout, a hard-coded timeout. So we distribute our scan target across 4 web workers. We only fetch the resource headers during the scan, and we implemented a hard timeout of 300 milliseconds, and we don't bother with the response body. So the timeout will drive how fast a scan can go. So the scanner will only spend a maximum of 300 milliseconds per target. If you get a fast response, then it will be lower than batch. If you don't get any response, for instance, because the port is firewalled, then you will have a hard limit of 300 milliseconds, and it will move on to a new target. So this is fast for open HTTP ports and for closed ports. Closed port because when you send a request to a closed port, you get the TCP/IP stack will respond immediately with a reset packet. So you're not going to linger here. It's slower for firewall ports because you don't get any response at all. So you're going to hit the limit of 300 milliseconds. It's obviously slow for slower HTTP service, and possibly a protocol like SSH, this kind of stuff, which are not speaking HTTP. So you want to use a lower timeout when you're scanning the LAN and fast HTTP service. You want to use higher timeouts when you're scanning different networks with a higher latency, such as a VPN. Other interesting piece of information, we use the WebRTC IP address leak when available. Is available on Chrome and Firefox to obtain the IP address of the target browser and try to derive a subnet that we can scan then with Singularity. We obviously use fetch with credentials omit. So when we do a scan of the network, there's no dialog box popping up, and that will inform the victim that the scan is ongoing. We're currently considering adding a second scan pass for potentially slower services. This is in our to-do list. So we have discussed how we made DNS rebinding attack more reliable, how we made them faster. We have means to scan for vulnerable services. So now we're going to show you how you can automate all what we have discussed to automatically detect and attack targets. So Singularity comes with auto attack HTML automation file. It is fully customizable. It allows you to leverage all the features that we have discussed so far. So you can choose a specific exploitation payload. For instance, you can target Ruby on Rails, or you can ask Singularity to auto-select the payloads based on the service it has detected. You can hard-code your target selection, or you can ask Singularity to search for more targets. Same thing for the ports, the services. You can configure your default DNS strategy and ask Singularity to optionally auto-optimize and find the best strategy to use in a specific case for faster rebinding. And obviously, you have all your options, such as flooding the DNS cache or hiding the activity from the user and so on. So we intend to implement more auto-optimization, so you don't have to read our extensive wiki. So when you're designing your attack, you want to mix and match different specifications of the same targets for the added reliability, to bypass security controls, and for speed. So as we discussed on the loopback interface, you can use 0.0.0, localhost, and 127. You can ask Singularity to find and use the external IP address to exploit the internal interface of your routers or Wi-Fi access points for a device that use the weak end system model. And I can only encourage you to look at the DEF CON talk in that manner to understand how it works. You should really do your homework and do some open source intelligence, try to determine how a corporate environment names their assets. So, and eventually use a dictionary of service name and try to specify them as a CNAME. So, for instance, jenkins.internal.corp.com. This is likely going to pay off. So we briefly mentioned service detection. So Singularity comes with a number of attack payloads targeting services such as Ruby on Rails or the AWS metadata instance. So we recently added a service detection routine to these payloads. So for instance, if Singularity detects that there is a HTTP header containing the value X Jenkins, it's more than likely that it is pointing against a Jenkins instance. So when you select the automatic payloads, Singularity will try to detect the service and automatically deliver the appropriate attack it has. With our tool, we were hoping to blur the lines of origin, and I think we have achieved that with Singularity of origin, hence the name. So how do you protect from DNS rebinding? So you often read or hear that you should use DNS blacklists, or sometimes people will answer tentatively, maybe you should consider DNSSEC, or use this DNS provider, or I bought this router, it states that it has DNS rebinding protection, so maybe you should consider this. Well, we learned that common wisdom is not enough. It's hard enough to understand all the subtleties of DNS rebinding, and to devise appropriate protection is not easy. And no, DNSSEC doesn't help in that case at all. So, Roger, what's the best way to remediate or protect against DNS rebinding?
So there are 3 separate ways to properly protect yourself. You can use TLS on your target service, even on services listening on the local host. You can require authentication. If the attacker doesn't know the password to access your service, they can't make valid requests. And you can validate the host header for incoming requests using a whitelist of trusted values such as localhost or 127.0.0.1. Remember, the origin in our demo still points to the attacker, and this won't be in this whitelist. There is also a proposal called Course RFC 1918, which would require a pre-flight course request for websites hosted on a public IP address, making a request to a private IP address. This is currently a draft and not shipped in browsers, but if it does, it can prevent DNS rebinding. We have one last live demo where we would like to show you how to automate this process. So previously, the victim was browsing to the Singularity manager web interface where they configured everything. That's not very realistic. So this time we start with a port scan. So the victim browses to Singularity, launch a port scan, discover listening ports on the local host, rebind to them in 3 seconds, auto-detect the services, and launch the exploit right away. So for our demo, we have a Rails console installed on the local host, port 3000, and the Jenkins instance on port 8080. So this is the victim browser, and we are now going to browse to this auto attack demo site. That's all the victim has to do, and then the attack launches automatically. So we see here that they already detected port 8080 and 3000. It tries to rebind to those. The rebinding was already successful after 3 seconds. It detected Jenkins and Rails. For Rails, we have code execution, the calculator, and for Jenkins, we are just dumping the plain text passwords stored in Jenkins. This is the source code of this auto attack script where we can configure what we would like to attack. So here we have the rebinding strategy. We can configure that. We can say which attack payload we want to use. So we say automatic. Automatic means it tries to automatically detect what's running on a service and exploit it if we have a payload available. We can specify the ports we want to scan, so it supports port ranges, but for this demo we only scan port 80, 80, and 3000 to make it fast. And then we can specify the target service. We use the 000 IP address for localhost. There are a few other configuration options, but none of them are required. You can get our slides on this URL. You can get Singularity on our GitHub page with all these features. And we should have some time for questions.
Okay, anybody have a question? Hands up, please.
How much of the prevention piece of this is just to not run web servers on your endpoints?
Well, so if you don't run any web server on your endpoints, then you're completely safe, yeah. So, but we found that especially in development or developer-oriented companies, kind of stuff, that's a lot of these services are running. The other aspect as well, if you have any service that is not running on your machine, but let's say you have a Jenkins instance running on your network, on your corporate network, and you don't have authentication set up, or you don't have HTTPS set up, then you'll be able to attack them using just the browser of the victim.
I take a look at a lot of thick client apps, and I'm just commenting on the thick client apps that I take a look at. Ones that you wouldn't imagine are web servers. So, yeah. I mean, this is broadened just beyond the core development group, but into more of just your everyday users. So I don't know if you had any commentary on the proliferation of web servers on computers.
Well, there is a proliferation of web servers in corporate environment. I think it's just down to the ease of implementing HTTP interface on your environment. The success of a framework like Electron.js, which make it easy to write an application for the web and for the desktop. Yeah, you're increasing your attack surface when you have a port listening, and you need to consider the pros and cons of doing that. Yeah. Any other question?
Going once, going twice. All right, I want to say thank you to Gerard and Roger. Thank you very much for a great talk.
Thank you.